there are a lot of methods for solving cubes. An example is the 3x3 and almost all its mods, which are solved L by L or layer by layer. I mean that we progressively solve all types of pieces from one pole of the cube to the other. The case is that for solving cubes we need a method which contains algorithms and, if necessary, algorithms for parities. Let's explain this further. First, I have to talk about the methods. I've classified them like this. As I mentioned, the layer by layer is one of the most common methods. We can use it in all the n by n cubes, all the megamixes and more cubes. As I mentioned, we solve from one pole to the other. In the megamix, for example, we solve one face and so we continue with the adjacent pieces until we reach the opposite face. In harder cubes, a very good method is solving it by hierarchy. I'm gonna explain this with some examples. In the Bohemian dodecahedron, we have to first put in place all these edges. After that, these petals, the centers, and finally these small triangles that are a big headache, trust in me. A subcategory that is totally solved by this method are the crazy cubes. For example, in the Crazy Megamix version 2, I first solved the internal edges, then the external edges, and the same with the corners. The point is that when we solve cubes by hierarchy, we solve all the pieces of one type, and then the same with another type of piece, and so on, returning to the geometrical shape. This isn't at all an entire method, but it's an important step in a lot of cubes. This consists in return to the geometrical shape, and then we continue with some of the previous methods. Some cubes in which we use this are the square 1, Sun Mom cube, Morpha-Aureola, the Picture Sanity, 4x4x6, Races of the Rhombus, and Dreidel cube. Reduction is a method that consists in convert an n by n cube to a lower degree n by n cube. For example, when we solve a 4x4, we normally reduce it to a 3x3 case. The same with the Pyramix 4x4, but this one is reduced to a Jinx Pyramix. This is not an entire method because it's only a step in a bigger method that uses layer by layer or hierarchy, but I consider it important enough to mention it. Now we're gonna talk about the algorithms. The algorithms are sequences of movements that have a specific goal, like turning edges, interchanging corners, etc. In my opinion, we can classify them in pure and impure algorithms. The pure algorithms are those who respect the orientation of the centers. They are called commutators and conjugates. Some of the most powerful algorithms are the pure cycles. I'm gonna make a cycle of these edges in this cube. First, we will make a double 2 cycle, a very normal algorithm in this cube family. We make an helicopter turn, and we do the opposite. Another example is this one. For making a 3 cycle of these pieces, I'll use an algorithm of this cube. I'll make a setup, I will explain this term later, and use the algorithm. Change the orientation of the center at the return, and there it is. Looking at it from the theoretical side, pure algorithms consist of making an alpha movement, a beta movement, alpha prime and beta prime. The impure algorithms are those that work in general situations, like this, and those who doesn't respect the centers. Almost all the speed cube algorithms are of this kind. For example, this perm, I don't remember the name, but it makes a cycle of 3 edges. What's happening here? If I do this same algorithm in a 3x3 with orientation of centers, the result is not so good. With a pure algorithm, this doesn't happen. unlike pure algorithms, in this case the path we give to the pieces is linear. That is what I call them impure. A very important part of the algorithms are the setups. Basically, they are accommodations prior to executing an algorithm. For example, if I want to cycle these 3 corners, I may think that I could use this algorithm. But one of the corners isn't in the same phase, so I can do a setup to force the case in which this algorithm is useful. Another example. All of you may know this case in the pyramids and the algorithm for solving it. So if I want to use the same algorithm, in this case, I will make this setup, and now is the case in which I can do the algorithm. Once executed, I have to undo the setup. Parities are a canon event in the life of all of we, some of them being not so difficult and others yes. The origin of this term in the cubing started with these situations that arise in the 4x4 when we solve it by reduction. Basically, they are situations apparently difficult that may or may not appear to us. They simply require us either one extra step with one more algorithm or a complete step backwards into resolution. And that depends because we have different types of parities, but I want to make an entire video of that. I'll explain this with an example. I don't even know if this is the red phase place, because in even n by n cubes we don't really have centers. We create them artificially, so to speak. So if this wasn't originally the red phase, the edges are not in a place where they should be in a case that we could solve with the 3x3 method. Another parities come in cubes with extra turns than the original version. In this case, the dreidel can rotate its corners and we can create this apparent parity. Something similar happens with the mix-up cube. Thank you very much for watching the video. The next one in English will be related because I will show you how to solve the 4x4 parities with my own method, which can be used in 4x4 mods with center orientation. So, see you soon!